When dealing with a 400 amp breaker tripping during a switch from generator to normal power, especially when automatic switchgear operates too quickly for ice cube timers to reset, several solutions can be considered. Firstly, extend the delay time on the ice cube timers. This involves increasing the duration the timers wait before allowing the equipment to restart after the power switches back to normal. By giving the timers more time, you ensure they fully reset before the load is reapplied, preventing the surge that causes the breaker to trip. Secondly, consider replacing the ice cube timers with memory relays. Unlike standard timers, memory relays retain their settings even during power interruptions. This means that when the automatic transfer switch operates, the memory relays will maintain their off state for the program duration, effectively resetting and preventing an immediate restart of the equipment upon the return of normal power. Thirdly, install a transfer delay module into the automatic transfer switch system. This module introduces a deliberate delay before the switch back to normal power occurs. The added delay provides ample time for the ice cube timers to reset, preventing the simultaneous startup of all connected equipment. This helps to avoid overloading the system and tripping the breaker. Fourthly, explore the option of splitting the load. Divide the equipment into smaller groups and connect each group to a separate timer. By distributing the load across multiple timers, you reduce the amount of current each timer handles. This allows each timer to reset more quickly, as they are not burdened with a large inrush current from multiple devices starting at once. Fifthly, for systems with large motors, install a variable frequency drive, or VFD. A VFD controls the startup current of motors, significantly reducing the inrush current experienced during motor startup. This reduction in inrush current allows the timers to reset without being overwhelmed by a sudden surge in power demand. Sixthly, install a soft start device for equipment with high inrush currents. A soft start device gradually increases the current supplied to the equipment during startup. This gradual increase prevents a sudden surge of current, reducing the load on the timers and allowing them to reset effectively. Seventhly, fine-tune the settings on the automatic transfer switch to optimize the transfer process. Adjusting parameters such as the transfer time or reducing the number of switching operations can minimize disturbances and give the timers more time to reset. Experiment with different settings to find the optimal configuration for the specific setup. Eighthly, consider a manual transfer switch. If possible, manually switch over from generator power to normal power. This approach provides greater control over the transfer process, allowing you to ensure the timers have reset completely before restoring power to the connected equipment. This eliminates the risk of a sudden surge causing the breaker to trip. Beyond these specific solutions, there are several general considerations to keep in mind. Understanding the load profile of the equipment is crucial. Identify the devices that draw the most current during startup and prioritize their delayed activation. Review the wiring and connections to ensure there are no loose connections or damaged wires that could contribute to the breaker tripping. Consult with a qualified electrician to assess the system and recommend the most appropriate solutions. They can perform load calculations, verify the proper operation of the automatic transfer switch, and ensure the electrical system is up to code. Also, it is important to ensure that the timers are properly rated for the voltage and current requirements of the connected equipment. Using undersized timers can lead to premature failure or malfunction, affecting the overall reliability of the system. Regularly inspect the timers for signs of wear or damage, and replace them as needed. It is also helpful to keep a detailed record of any changes made to the system, including timer settings, wiring modifications, and equipment upgrades. This documentation can be invaluable for troubleshooting future problems and ensuring the system operates safely and efficiently. If the issue persists after implementing these solutions, consider conducting a power quality analysis. This involves monitoring the voltage, current, and frequency of the electrical system to identify any anomalies that could be contributing to the breaker tripping. A power quality analyzer can detect issues such as voltage sags, harmonic distortion, and transient surges, which may not be immediately apparent. Based on the results of the power quality analysis, additional measures can be taken to mitigate these issues, such as installing surge protectors, harmonic filters, or voltage regulators. These devices can improve the overall stability and reliability of the electrical system, reducing the likelihood of breaker tripping. In addition, it is important to ensure that the generator is properly sized for the load it is intended to support. An undersized generator may struggle to provide sufficient power during the transfer process, leading to voltage drops and breaker tripping. Consult with a generator specialist to determine the appropriate generator size for the specific application. Regularly test the automatic transfer switch and generator to ensure they are functioning correctly. This includes verifying that the transfer switch operates smoothly and that the generator starts up and provides stable power output. Regular testing can help identify potential problems before they lead to breaker tripping or other equipment failures. Furthermore, consider the impact of environmental factors on the electrical system. Extreme temperatures, humidity, and dust can all affect the performance of electrical components. Ensure that the equipment is properly ventilated and protected from the elements. If necessary, install environmental control systems to maintain optimal operating conditions. It's also beneficial to implement a preventive maintenance program for the electrical system. This includes regularly inspecting and cleaning electrical panels, tightening connections, and testing protective devices. A well-maintained electrical system is less likely to experience problems that could lead to a breaker tripping. Should the problem persist, exploring advanced control strategies might be necessary. Consider implementing a programmable logic controller, or PLC, to manage the transfer process. A PLC can provide precise control over the timing and sequencing of events, ensuring that the equipment starts up in a controlled manner. This can minimize the inrush current and prevent the breaker from tripping. Lastly, engaging with the equipment manufacturers to understand the specific power requirements and startup characteristics of the connected devices can be beneficial. They may be able to provide recommendations for optimizing the system and preventing breaker tripping. By systematically addressing each of these potential causes and implementing the appropriate solutions, it is possible to resolve the issue of a 400 amp breaker tripping during the transfer from generator to normal power. Remember to prioritize safety and consult with qualified professionals throughout the process.